So what the heck are quantum numbers? In reality, although it sounds really scary, they are just a fancy way of giving the address of an electron, where an electron is. In particular, it's kind of showing us which orbital or home an electron is in. It's very similar to longitude and latitude. So if you're a geography buff, you'll see that longitude and latitude can take us to a specific point on a map. Similarly, these four quantum numbers we're going to talk about can locate for us where an electron is in any particular orbital. The one tricky thing is that even if we are able to get to the orbital location, we can never know exactly where in the atom the electron is. I'd be remiss if I didn't give you another analogy here, and the analogy is simply that quantum numbers are kind of like an address. So if you were to address an envelope, which I'm sure that all of you are probably not as familiar with as us old folks are, but you put down a state, and then you put down the zip code, and then the city, and then the street, and then the house. But never on that do you then write kitchen, because there's no way in the world they're going to know exactly where in the house you are. And I do understand that when you write an address, you kind of go the reverse of that order. But when they're reading it, let's be honest, the Amazon guy is reading it, he's going from the farthest or widest to the narrowest point of view. Well, that's kind of what happens. That's kind of the same deal in an atom. We're going to be able to locate all the way down to the orbital that an electron's in, but we're never going to be able to determine exactly where in that orbital the electron is located. And that's actually called the Heisenberg uncertainty principle. Now, you may be familiar with the guy on the left, but the handsome fellow on the right, he's the actual guy who is Heisenberg, and he came up with this really scary-looking formula which you need to know nothing about. What you do need to know is simply this, that the Heisenberg uncertainty principle says you cannot know both the velocity and the location of an electron at the same time, which essentially says when you have an orbital where the electron lives, you can't really know where in that orbital it exists. So we're going to move ahead and we're going to start talking about quantum numbers. And there are four quantum numbers, and each of these four quantum numbers, they are locators as to where the electron is in an atom. And each one has a particular meaning. So the first quantum number, we actually will sometimes call it the first quantum number, is actually known as the principal quantum number. And it has the symbol n. So instead of saying the first quantum number, sometimes we will just say n equals, and we'll say whatever number it is. The meaning of the quantum number is actually the most important thing. It tells us the main energy level where an electron is found. There are only 7 main energy levels in an atom, so the values for n can simply be 1 through 7. So if I were to say to you n equals 5, what that means is that the electron I'm looking for is found in the 5th energy level. So first quantum number is called the principal quantum number. It has the symbol n. The second quantum number is called the angular momentum quantum number, which is really a mouthful. So sometimes we kind of shortcut it and we call it the orbital quantum number. So you may get away with saying that. And the orbital quantum number, it also has a symbol that represents it, and it's this cursive L. So instead of saying the second quantum number, or the angular momentum quantum number, or the orbital quantum number, we can just say L equals. Now, what does the angular momentum quantum number tell us? It tells us the shape of the orbital where the electron is located. Now, you may remember this from before, but there are 4 shapes: S, P, D, and F. I think we came up with a couple of acronyms to help us out. Stupid people die first. But here's the problem, is that we are dealing with quantum numbers. And I'm going to box the word numbers because what I'm showing you right here are letters. So the second quantum number cannot be S or P or D or F. So we have to translate it into numbers. And so we have this ingenious code, see if you can crack it. S is 0, P is 1, D is 2, and F is 3. So if I were to tell you that my L is 2, what that would mean is that the orbital that my electron is in a d orbital. Now, combined with the first quantum number, if I said n equals 5, L equals 2, what I'm telling you is that the electron that we're looking for is in the 5th energy level, and it's in a D-shaped orbital. Now, if you take a look at your periodic table, and now that you're familiar with how the periodic table works, you can actually see that there's only one row of 10 possible choices that could be a d orbital in the 5th energy level, right across the center of the periodic table. So we're really narrowing down where that electron might be. Now, just to remind you what the shapes look like, I'm going to quickly go through them. This S-shaped orbital looks like a sphere. And I always wondered why they started with 0 instead of starting with 1, because I would have numbered them 1, 2, 3, 4. The closest I can tell is that they probably started with S as a 0, simply because maybe this looks kind of like a 0. I don't know. But S orbitals have a sphere shape, and they have the second quantum number, L equals 0. P orbitals, they always come in a set of 3. They have this kind of like this double-lobed peanut shape, and their L is equal to 1. So that's a quick way of saying these are p orbitals. D orbitals come in a set of 5, as we see down below here, and their L is equal to 2. And again, they look kind of like these double-lobed things. They're kind of crazy looking. And then F orbitals, they're just outrageous. We say their L is equal to 3. Now, we're going to talk about how it's important that there's actually 7 orbitals in a set of F orbitals, etc., when we deal with the next quantum number. But just be aware of the 4 different shapes. Sphere, kind of peanut looking, maybe like a daisy, and way too complex. And just as a reminder here, our code is 0 is the number that represents S, 1 is represented by P, D is represented by 2, F is represented by 3. I'm going to scribble out this G right here because mathematically it exists, but for us right now, these are not the droids you're looking for. Now, let's go to the third quantum number. And the third quantum number is called the magnetic quantum number. And it actually has a symbol, capital M, with a cursive L. And what does it tell us? Well, it tells us when we have a set of orbitals, which orbital in that set the electron we're looking for is in. The actual technical definition is this. It tells the orientation of the orbital around the nucleus, but that's not too much help for us. Now, how do the numbers work and how does this work? Well, let's backtrack a little bit here and let's talk about the first 2 quantum numbers. The first quantum number, n, it tells us the main energy level, and let's say that my n was equal to 5. Wouldn't that tell us that the electron we have is in the 5th energy level? If I then said that my L is equal to 1, the second quantum number, that would tell us that the electron is in a p-shaped orbital. The ML tells us which in that set of p orbitals my electron is in. So in order to do this, I'm going to demonstrate it by using this kind of pyramid graph. So if you take a look, each one of these sets of orbitals, all 3 of these, actually all 4 of them, they are odd numbered. And so the way we could number them, or we could label them px, py, and pz. And if you take a look at some of the actual names, let me go backwards here. I don't know if you can see this, but if you could read what the actual graphical names are for these, they're crazy. So we don't want to use those, and plus they're not just numbers. So instead what we're going to do is we're going to use number line theory. So what we do is we take the middle orbital, we're going to do the p orbitals first, and we take the middle orbital and we number it 0. And then we number line it. To the left-hand side, we go minus, and to the right-hand side, we go plus. So the first orbital that we put electrons in is going to be the -1, then the 0, then the +1. And since we can put 2 electrons into any set of orbitals, the way we would put electrons in is we would put 1 in here, then 1 in here, then 1 in here, and then go back and go 1 here, 1 here, and 1 here. In other words, we'd go 1 electron in the -1 orbital, then the 0, then the +1, and then back again, -1, 0, 1. It'd be the same as counting on your fingers and going, all right, I put an electron here, then here, then here, and go back and do it again. The way we number it is the middle orbital always is a 0, and then we go -1, 0, 1, -1, 0, 1. But what if you have d orbitals? Well, again, our middle orbital, if you held up 5 fingers to represent 5 d orbitals, the middle orbital is a 0, and we go -1 and -2. So the very first orbital we're going to put electrons in is the minus 2. We're going to go minus 2, minus 1, 0, 1, 2. And then we're going to go back and put a second electron in going minus 2, minus 1, 0, 1, 2. So how does that look when we're actually doing it on our diagrams? Well, this is going to be a 0. This is going to be a minus 1, and this is going to be a minus 2. This is going to be a plus 1, and this is going to be a plus 2. Similarly, if you take a look at our f orbitals, conveniently there is an odd number, 7, and the way it numbers is going to be 0, minus 1, minus 2, minus 3, and over here it's going to be plus 1, plus 2, plus 3. So how does this work if we were just talking about quantum numbers? So let's say I'm using the same example as we did before. N equals 5. Well, that means my electron's in the 5th energy level, as we've discussed. If I say L is equal to 2, what that now means is that this is in a set of d orbitals, in 5 of them. My last quantum number, if I say ML is equal to minus 1, what that means is that in this set of 5 orbitals down here, it would be in this second orbital. Now, that still doesn't tell us whether or not it's the first or second electron into that orbital, and that's what the 4th quantum number is going to tell us. But whenever you're thinking about the 3rd quantum number, it's essentially telling us which one in a set of equal energy orbitals our electron is in. Let's go to the last quantum number, which we call the 4th quantum number. It's called the spin quantum number, and it has this kind of a weird symbol, M subscript S. And it has 2 values, plus 1/2 and minus 1/2, which are kind of weird, and we'll get to in a little bit second. But what is that? What do the spin quantum numbers tell us? Well, it tells us whether or not an electron is the first or second electron in an orbital. So essentially what we know is this, that whenever we have let's say a set of p orbitals, let's pretend that these are 2 p orbitals, this is an orbital notation. There is other stuff over here, but we don't really care. When we put electrons in, we go 1, 2, 3, and then don't we go back and go 4, 5, 6? So we have to differentiate between these 2, the first one in and the second one in. And so what we do is we say that the first electron in, its 4th quantum number, or its ms, is a plus 1/2. The second electron in, its ms, is negative 1/2. So it's a quick way for us to determine whether or not an electron's the first in an orbital or a second. Now the reasoning behind plus 1/2 and minus 1/2, well, if you take a look at these diagrams, the first electron in a particular orbital, it spins in one direction, right? The second electron in spins in the opposite direction. And that's probably why they went plus 1/2 and minus 1/2, and they probably chose 1/2 instead of 1 and 2, because each electron is half of the total number that you can have. Now, how does this play out and what does this really mean? So let's look at some sets of quantum numbers and see whether or not we can make sense of them. So let's say I gave you these 4 quantum numbers. N equals 3, L equals 2, ML equals 1, and MS equals negative 1/2. What would that really mean? Well, this 3 would tell us that the electron was in the 3rd energy level. This 2 would tell us that the electron was in a d orbital. This 1 would say in our set of 5 orbitals, these are all d orbitals, if I were counting them out, it goes minus 2, minus 1, 0, 1, 2. It would mean the electron we're looking for is right here. And this minus 1/2 means that it's not the first electron in this orbital, it's the second one. Yeah? Let's pretend I gave you this configuration. If I gave you and I asked you to give me the 4 quantum numbers for the very last electron we put in here. So, if I were looking at this, I could go, all right, well, N is going to be 3 because the last electron is in the 3rd energy level. So N is equal to 3. My L, since this is a d orbital, and remember how the shapes go, it goes S, P, D, F are 0, 1, 2, 3. My L, in this case, since this is D, would be equal to 2. And here's where you can either do this on your fingers or you can draw them out. But d orbitals come in a set of 5. So if I have 5 electrons that I'm placing, wouldn't we place them like this? 1, 2, 3, 4, 5. So wouldn't this be the electron that we're dealing with here? So if we took a look at which orbital it's in, this is a 0. This is going to be -1. This is going to be -2. This is going to be +1. This is going to be +2. And our ml, in this case, would be +2. And then the last quantum number, the ms, it asks us whether or not it's the first or second electron that's in that orbital. And since this is the only electron in that orbital, it's the first one in there, and we're going to say it's +1/2. Let's try one more. What if I gave you something that looked like this? Give me the 4 quantum numbers for this. Well, let's take a look. We know that the last electron, and when we say give me the 4 quantum numbers, do you realize that every single electron in this is going to have a set of 4 quantum numbers? The Pauli exclusion principle, it's actually a rule that says that every individual electron in an atom has a set of 4. So when I say give me the 4 quantum numbers for this, I'm asking you for the 4 quantum numbers for the very last electron. So if I take a look at this, wouldn't it be n equals 5? Since it's a p-shaped orbital, I go L is equal to 1. And if I, in my mind, thought, well, there's 3 of them here, the middle orbital is 0, this is a -1, this is a +1, wouldn't, if I was filling them in, 1, 2, 3, wouldn't it be in the +1? So I go ml is equal to +1. And then lastly, is it the first or second electron in there? Well, it's the first electron in there, so my ms would be equal to +1/2. Now, one of the ways that we say this often is this: give me the 4 quantum numbers for the last electron in bromine. Well, in order to do that, we need to know what the electron configuration is for bromine. Unfortunately, we have the periodic table that can help us, and if we were to draw it out, it would be Ar, (4p5). So Ar, 4s2, 3d10, 4p5. And again, we're looking for the very last electron we've placed in here, and we would be able to go n equals 4, because it's in the 4th energy level. The p, just like we did before, the p is, its L value is going to be 1. And if we have 3 orbitals here that are 0, -1, and 1, and we put in 5, 1, 2, 3, 4, 5, wouldn't this be the electron that we're looking at here? So wouldn't the ml, the orbital that it's in, wouldn't it be 0? And wouldn't this be the second electron that we put in here? So hopefully this has given you a little bit of practice and something that you can work with, and we will do a little bit more in class. And I'm going to also show you how to use your periodic table to do quantum numbers way, way easier. Hope this has helped.